Alright, in this video in section 13.6 we're going to look at some of the key geometric properties of the gradient vector. And in the last video we looked at question number 4 and we saw that the gradient vector at a point was perpendicular to the level curve of our function that passed through that point. And I had said that that was a generalizable result. Okay, and so that's actually the content of the first theorem here we're going to prove, which says that if f is differentiable at a point P with coordinates a, b, and the gradient is not 0, so it's not the 0 vector, then the gradient is perpendicular to the level curve of f through P. Alright, so here below I have some level curves of our function, and I have our point P labeled here. So this is the level curve that passes through our point P, and I'll go ahead and refer to this particular level curve is, say, f of x y is equal to c. Okay, so we want to think about all of these points on the level curve as the projections of the points up on our surface that are all at this altitude z equals c. So put another way, if I were to walk along the path on my surface directly above the level curve, my altitude would never change. Okay, so what I'm going to do here, I'm going to go ahead and draw a vector u that runs tangent to this level curve. So let's let u be a unit vector tangent to the level curve f of xy is equal to c. As I just said, right, if I walk along this path, this level curve, I'm not going to change my altitude at all. So if I was at the point P and I decided, okay, I'm going to walk in the direction of u, right, then at least, right, on an infinitesimal level, I'm going to stay on this path. And so my altitude will not change. Okay, so put another way, then we can say the directional derivative of our function f at the point AB in this tangential direction, u, would be 0, right? Why? Well, because if I stay on the path, right, then I'm not going to change my altitude. So here I would say there's no change in altitude along the level curve. Okay, but that then would imply, since I can compute the directional derivative in terms of the gradient, this implies that the dot product of our gradient and this tangential unit vector u would be 0. But if you recall from Calc 3, right, the dot product of two vectors equaling 0 would imply that these vectors are in fact orthogonal, or in other words perpendicular. Those are synonymous, and this little upside down t, by the way, just means perpendicular. And I also want to point out here, right, that this condition that the gradient vector is not the 0 vector comes into play right here, right? If the gradient vector were 0 itself, then saying that this dot product implies this perpendicularity would not be true, right? Because this would just be the 0 vector itself, right? But if this thing is not 0, and u is certainly not 0, it's a unit vector, then this is true, okay? All right, but then lastly, what we can say is that, look, if the gradient is perpendicular to this vector u, and u is tangent to the level curve, that must mean then that the gradient is perpendicular. This is perpendicular to the level curve f of xy equals c at the point P. All right, and that is exactly what we set out to prove. That is the end of the proof. Okay, great. So now let's go ahead and look at a variation of this and kind of build on that last theorem and look at this next theorem. This says if f is differentiable at the point P, and again the gradient is not the zero vector, then the gradient points in the direction of the maximum rate of increase of f at the point P, and the maximum rate of change of the function f at the point P is equal to the magnitude of the gradient. All right, so again I have some level curves for our function here, and to kind of help us get some intuition for what this statement is really saying, I'm going to go ahead just to illustrate. Let's say this level curve here corresponds to all points on our surface that are at an altitude of, say, 2 units. And then this is the level curve for all points at an altitude of 4 units, and then 6 units, so on and so forth. And let's say we're at this point right here, call this point P. Okay. So if I'm at the point P, let's say I now want to choose some direction to walk in to increase my altitude, okay? And furthermore, if I wanted to know, hey, what direction should I move in so my altitude should increase as fast as possible, right? Where should I move, right? Well, if I want to increase my altitude, I should start heading towards, right, this outer contour, right, that has an altitude of 6. How should I get there if I want to increase the altitude at the fastest rate? Well, if you give that a little bit of thought, right, we want to head directly towards that contour. Or put another way, right, we want to head in this direction. That would be orthogonal to this level curve that passes through the point P, right? That is the intuition. We're saying if I want to increase my altitude as fast as possible, I should head directly towards, right, this outer contour, and that's going to correspond to heading in this direction that would be orthogonal to this level curve that's passing through P. Okay, so that's the intuition. That's ultimately, though, what we want to now make a little more rigorous. Okay, so here's what we'll do. We'll go ahead and say, all right, let's say I'm just going to choose an arbitrary direction for the moment, and I want to compute the rate of change in my altitude as I move in that direction. Well, that's what the directional derivative does, right? And this thing is the dot product of our gradient vector and the direction vector I choose to move in. And now, if you recall again from Calc 3, dot products can be computed in terms of magnitudes. This would be the product of the magnitudes of these two vectors times the cosine of the angle between the two vectors. Okay, so over here what I'm going to do is just draw a little side picture to help us. And let's say here is our level curve. All right, and so now here I am at P. Here is our gradient. And we know that this thing again is from the last theorem. We know that this is perpendicular. And let's say I'm choosing to move in this direction, say U. The question we want to answer now is, how should I choose this vector U, right? So this directional derivative will be as large as possible. And this angle theta here, when you see in the cosine, that is referring to sorry, the angle between these two vectors. All right, so now the other thing to note here, what's the magnitude of the unit vector? Well, it's a unit vector, right? So that's 1. So this, in fact, is equal to the magnitude of our gradient times the cosine of theta. Okay, so if I want this thing to be as large as possible, what do I want? I want the cosine to be as large as possible, right? Because basically the idea is I can change u by just changing this angle, right? And so if I want to make this overall expression as large as possible, make that cosine as large as possible. And how big and how small can cosine be? Well, it's bounded between -1 and 1. So what we're saying here is that the maximum value of our directional derivative, this thing will equal the magnitude of our gradient times the maximum value of the cosine, which is just 1, right? And when does the cosine of theta equal 1? Cosine of theta is equal to 1 when theta is equal to 0. Okay? And if I choose theta equals 0, that means, right, the direction I'm going to move in is exactly the direction of the gradient, right? So to finish, we're going to say the maximum value of this rate of change is, in fact, the magnitude of the gradient, and this occurs when u points in the direction of the gradient. Okay, and that really does it, okay? Because again, we were seeking to prove these two statements, right? That the gradient points in the direction of the maximum rate of increase. Well, that's exactly what we just said here. And the maximum rate of change of f is equal to the magnitude of the gradient. And that's exactly what we're saying here, right? The magnitude of the gradient times 1 is just equal to the magnitude of the gradient. So that's going to do it. The last thing I'll say here before moving on, notice if I set theta equal to 90 degrees, right? What's the cosine of 90? It's 0. And so what would that be saying? It'd be saying that my directional derivative would be 0 when theta is 90 degrees. Oh, that means when I move tangent to my level curve. That's exactly what we were saying back when we proved Theorem 1. Pretty cool, huh? All right, cool. So now what we'll do for the very last thing is just summarize everything we've just discussed. Okay, so first up, we can say that the direction of the gradient is perpendicular to the level curve of f through our point P, and it's in the direction of the maximum rate of increase of our function at P. And then lastly, the magnitude of the gradient is the maximum rate of change of our function at the point P. All right, in the next video, we will see all of this in action. See you there.